mass spectra from powering multiplexed DNA proteomics. We've just heard about the real opportunities and capabilities that PSN tag offers in terms of the number of parallel samples we can analyze together. Well, I want to talk a bit about how we actually go about searching that kind of data. What are the challenges that this kind of multiplexity creates, or what are the actual structures within the data that we can utilize that we can help search this kind of data? So once again, we refer to our period. And like was said previously, we can typically parallelize a number of samples. We might do this in a PDA context, where we can get up to 35 plex. But this is, again, as was said, sampling one peptide at a time. We could parallelize the number of peptides in the DIA context. We can sample multiple peptides per scan. But the level of multiplexing in this domain has been somewhat limited to date. But now with PSN tag, we can start to scale here. So as we multiplex in this domain, we are going to sample all these peptides, but we ought to make sure we still identified it. So as we increase applying this pyramid, we don't want to sacrifice the number of peptides we're identifying, that proteome depth, as was talked about it. And as we increase the number of samples, we want to maintain both of these to keep our equation of throughput true. So just to give a slight bit of background, this is probably known to a lot of people here, but just to get everyone up to speed. In bottom-up proteomics, we typically couple a mass spectrometer to an LZ system, which separates our peptides in type. And then our mass spectrometer will separate them in the mass to charge domain. And so we get this ion map of peptides, different molecules that are separated in mass and time. All we want to do is we want to sample these. As was said previously, we sample a section of these fragments or a sample of these ions, and we send them to fragmentation, and we can do identification that way. And just to talk about these funny shapes, we see these parallel lines. Well, these are actually the isotopic envelopes we see. And I want to talk about this because we don't isolate a single ion for every peptide, particularly in DIA mass spectrometry. We sample the full isotopic envelope, and this will become pretty relevant later on. So the different ways we sample this ion map, as I said, we can do it a data-dependent acquisition method, where we take a survey MS1 scan, and then based on the ions we see, we can then isolate those and send those for fragmentation. But you can see how this is a pretty sparse sampling of our full ion map. And we want to, there are alternative approaches like data-independent acquisition, which gave us a greater sampling. So we take this MS1 scan, and then we have repetitive cycles of these windows in every duty cycle. And you can see the relative size of these windows is much larger. So we're sampling more ions, potentially multiple peptides per scan. We also have the additional dimension that we sample the same peptide multiple times. So we get this, we can capture that as it elutes off the column at different points in time. But because we have multiple peptides in a single spectrum, it's not able to it's not simple to disentangle what fragments came from which. So in the examples that were shown previously, it was a DBA spectrum where all the fragments are assumed to come from a single peptide. What happens and how do we search data when that is not the case? So this is the case, cartoon version of what was shown previously. We observe some fragments, some piece in M/Z space, and we have a library of peptides we've seen before. So we want to assign with some level of confidence, okay, this looks similar to this one I've seen before, and with some level of confidence say, okay, we've identified this peptide. In a data-independent acquisition scheme, it become more complex. So we have multiple peptides. Potentially, all of these can be present. But how do we disentangle this mess that we see? Some peptides, as we can see, have a single source. We're not sure which source they came from. We can see here in this cartoon. But these are not labeled when they come off an each other. But the most important case here is some fragments can come from multiple sources. So they can be a superposition of contributions from the different peptides that were collated. And we can look at the rate of this, so how many peaks are considered distinct for each peptide, each precursor. And when I say precursor, I should note, to limit up the jargon, when I say precursors, it's a peptide with a given charge state. And so what fraction of those fragments are distinct for a given peptide? Well, we do this with in silico with a set of observed peptides we've seen previously, about 70,000. and we look at what fragments are distinct, and we see that most fragments for most peptides are actually not distinct, and this is a label-free DIA experiment. These are 16 Thomson-wide windows. Never for these are 60 Thomson-wide windows, so not that large. We can see as we increase the size of these windows, the number of distinct beats actually goes down. And you can say, well, why do we care if we increase the size of our windows? Well, in a single-cell proteomics example, maybe we want to capture more of the ions. So with smaller windows, you actually throw away most of your ions. In the larger window, you can actually capture more at the greater fraction of the ions. Or you could actually increase your sampling rate. So you could, with larger windows, you may want to sample your ion or your lesion beat more frequently, and that's afforded by using larger windows. And those window sizes are just based on dividing this mass range into these sizes. So we've an exponential increase, and we see that decrease. So, okay, many beats are distinct. This is labor-free. When we're here, ETR are interested in multiplex. So we want to scale this up. We don't want to deal into a labor-free. We want to increase the throughput. So if we were to multiplex and analyze the Barrett tags, this is the effect on these overlapping beats. So we get even fewer and fewer distinct peaks as we go from 3-plex, labor-free, to a 3-plex DIA to a 6-plex DIA. And so this level of overlap is inevitable as we increase multiplex. And so what we want to ask the question is, how can we handle these data? What is the best methodologies we can set up where we can deal with this data, this inevitable increase in overlap? So there are different ways you could deal with this. We could throw out overlapping signal. Of course, this is not ideal, given that we'll be left with very few as we multiplex to even greater amounts. And we could assign to a single precursor through competition. So if a fragment is potentially shared, maybe we only wanted to give it to use it to assign confidence to an individual precursor. Or maybe we could just model it. So we can accept this overlap happens. It's going to increase. And so let's try and deal with it. Let's take the data for what it is and try and model it. So this is the strategy we decided to use as we develop our software here. So what we're doing here at PTR is we're developing this framework. We're calling it Jmod, standing for Joint Modeling of DIA Spectra. And the goal of this framework is to support multiplex. We want to enable the increased throughput. I'm going to talk to you today about one method of that in the terms of as we multiplex in the mass tooling. But this framework can work from any type of multiplexing, and there are other types you'll hear about later, and we are pursuing as well. And also, we want it to be open source. So we want people that are using this, researchers, how are your data generated? We want you to be able to see the code, see the software, how it works, and how it's generating your data. And the people can collaborate. So maybe there's a research group out there that can use this as a foundation to address the challenges that are unique to their lab. And we open and welcome collaboration if people are interested in doing this also. So just to talk about this a bit more, in terms of this is conceptually what the problem is. We had this superposition of fragments and a set of library spectra that compose it. How do we go about disentangling this? So what we can do is we can set up our equation here. We start off with our observed spectrum. So we have our matched peaks as a list of observed intensities. So we could just, we don't need to worry about M over Z. The M over Z can be done for matching, but so we have a list of observed intensities that we want to model. And in our library, we ideally have all possible peptides, all possible spectra that could be contributing to this signal. And so what we do is we just fill in the columns of this matrix with our observed spectra. And each row here will correspond to each row here is a fragment in our library that is matched to this particular observed peak. If it does not match, we can just fill it with a 0. And the question is, can we find some set of coefficients that balance this equation? When we multiply our library intensities by this set of coefficients, can we get back our observed spec? So essentially, you'll be doing, if you remember your matrix or your linear algebra, each row by column. So this will end up all be multiplied by the single coefficient. And so what we get back is if we can find the set of coefficients, is this particular one will give you the abundance of this library spectrum in our observed spectrum. And we can do this for all the independent and individual spectra that we observe off mass spectrometer. And so we get a set of coefficients for each of these particular peptides, and we can trace out their elution curve and their abundances in the spectrum. And so if we want to find the set of coefficients, we just want to minimize the residuals. So multiplying these two together will give us a vector, and we can minimize the residuals between this side of the equation and this side of the equation and find the set of coefficients that does so. So let's look at a real example. So here, to simplify and make it observable, I'm looking at the monoisotopic peaks. So no isotopes here, and of observed peaks matched to these two very similar peptides. These two peptides differ by one amino acid, and I alluded to earlier, then they will share a lot of the same fragments. And so you can see here, using this joint modeling approach, we can deconvolve the signal, and so we can see we can actually attribute the intensities to individual fragments, so fragments that are just attributed to one peptide. But importantly here, we can model this superposition of fragment intensities that happen when both peptides contribute to a now. But this is label free. This approach is used by others. It's not unique to us. Specht, Chimeras, Pioneer all use this approach. What we want to do is we want to utilize this in terms of multiplex. As we increase this level of overlap, how can we use this to get still accurate quantitation and identification? So we started evaluating it with PSN tag. So as you see before, this is PSN tag here on the left. And all the dopable sites you can see where ions or isotopes can be added. And that gives us these 9 possible configurations of the tag. And so this evaluation we can do is we can look at this in context of a single channel. If we only treat a sample using just the delta 0, the base tag. Or we can set up this 5-plex example. So as was alluded to earlier as well, typically in DIA mass spectrometry, when we're multiplexing, we ensure that there are 4 Daltons between each channel, each sample. And this is to account for the isotopic overlap. It makes our lives a lot simpler, and most algorithms can work with the data if there's little to no overlap between these channels. And 4 Dalton achieve that. But if we were to relax that constraint, and we were to able to develop models that could, even if we just relax that to 2 Daltons and develop models, we would know almost double the effective throughput we could get for the same molecule. So this is where joint modeling goes up. We start off with this biplex example. So you can see here, the different isotopic envelopes. This is the observed MS1 intensities for this particular peptide. And you can see with joint modeling, we can get back these intensities by finding coefficients at the MS1 level now that match the expected or theoretical isotopic envelope to the observed data in the same way. But in the case of our 9-plex, now we don't have discernible differences in the isotopic envelope. And so we rely on this joint modeling approach. We could get back the individual contributions from each of the different channels, each of the different samples. And so in a biological context, these will be peptides from different samples. And what we can do is we can get back the individual contributions from each sample and thereby quantify the peptide distinctly in each sample by deconvoluting these peaks. So in the context of the number of identifications we can get, so this is the number of protein IDs we are getting for a 200 picogram sample on the Orbitrol Astral. So the Astral, for assuming 200 picograms, is typically how we use to model a single cell level input. It's pretty low. And you can see for label-free, we're getting over 4,000 proteins, slightly fewer for delta 0. But what's important here is that we are scaling. So we're not, when you remember that pyramid, as we increase the throughput, as we increase the number of samples we are analyzing in parallel, we are not sacrificing the level of depth for this particular type that we're doing. We are scaling multiplicatively with the number of proteins. And so to compare this to Diane for the same data, Diane is getting about 5,000 IDs and about 4,000 IDs or fewer. We got to 0 on the 5-plex. But important here, Diane or no other search engine can search this 9-plex data. So Jmod is unique in its current abilities to search this data. So no other search algorithm could give you this level of throughput for this data. And so IDs are not everything. also care about quantitation. It's very important that if you observe a peptide or a protein, how abundant is it relative to the other sites. And so to do this, we set up a mixed species where we mix human and these proteomes together. This is typical in the Proteomics community. Say it's similar to a spiking, where we have known input amounts of human where in each mixture. We have 200 picograms in A through D. But in yeast, we have varying amounts where we have from little as 20 picograms, 80 picograms in these sites. So that gives us 4 different mixtures we can use. With PSN tag, we have 9 different configurations for our tag, 0 through 16, every step in 1. And so we just label each of the different mixtures with these different tags, with these different configurations. And these are then mixed into one, run through a mass spectrometer, and so we can search the data and try and evaluate, can we get back these known ratios once we search the data. And so I'm showing you a 5-plex peptide before. This is a human. Obviously, DFES, we can see the similar abundances for each of the 5 channels. But if you have a yeast peptide, you can see how this changes dramatically and how now the contributions from a pretty abundant channel can actually significantly contribute to the abundances of the delta 12 channel in this case. And so this is where joint modeling becomes so important. This case is a particularly hard example where it just shows how joint modeling can be applicable even to the 4 Dalton states, which is typical for DIA multiplexed. And so what we can do is we can take all of the delta zeros and all of the delta 12s and compare them. They should have a 4-to-1 ratio. And on a log scale, you can see how the yeast peptides in this context all get accurate quantitation, or not all accurate, but there is accurate quantitation for the majority of these yeast peptides, and humans are centered at 0, so on a log scale, they have a 1-to-1 ratio. We could do this more systematically, so we can look at all the different mixture levels and collapsing, so all the A over Bs that are in this data, and compare that to the theoretical mixing ratios. And we could do this for all of the different combinations. So now we have all the different channels and their mixtures shown here on the data for the 5-plex 4 Dalton, and we can compare that to Diane. So Diane, as I said, is the leading search engine in this space. And you can see how we're getting similar, if not better, quant for these are intersected peptides. So there's no, these are the same peptides identified in this 5-plex experiment between both Jmod and Diane, and we're getting similar, if not better, quantitative accuracy. But of course, that's with 4 Dalton offsets. What about the case when we have much greater overlap? So I showed you, as I said previously, the human example. This was a significant signal in each of our channels. We could deconvolve this. You can see how challenges may appear at first when you have the yeast peptide, and you can see how the different input amounts, again, if we refer back to delta 12, it never contributes more than half of the signal to any of the ions it's matched. And so we can evaluate the quantitative performance of the 9-plex. And so here I compared it to a 5-plex, this is for using Jmod, the 4 Dalton offsets, and the 9-plex with the 2 Dalton offsets. And you can see for these examples, we're getting quantitative accuracy centered around the expected mixing ratios. And it's pretty comparable between both. So we've halved the distance, we've doubled the overlap, if not more. We doubled our throughput, we maintain quantitative accuracy in these data. And so we can focus in on these 2 particular examples. So this is the 4-to-1, this is the largest ratio we have in this particular data we was up. And you can see a direct comparison where they're comparable quantitative accuracy between both methods. And to zoom in on those 2 again, so we look again at our delta 0 versus delta 12 here for the 5-plex, and the delta 0 versus delta 12 for the 9-plex. And you can see how they're pretty comparable in terms of the accuracy of quantitation. But just to refer back to what's actually happening here, so this delta 12 is being pulled out of this signal. So we're really powerful, this joint modeling approach, how it can actually get accurate signal from this, and thereby double almost effectively the throughput we can get for the same molecule. Now, talking about PSN tag, I talked about the Astral. What about other approaches? So there are alternative tags such as diethylation, where we add FL groups of the primary amines of our amino acids, or our canovides, excuse me. And depending on the reagents you have available, this can achieve a 6 to 8 flex with 2 Dalton offsets if using TRIPS. This has been done before with DDA. It has never been done or utilized with DIA before. But Jmod and his joint modeling has this natural ability to deal with this data similar as I showed. One of the things to know with diethylation is to get this level of multiplexing, one must use deuterium. Deuterium affects chromatography and therefore retention tides. And so while with PSM tag, you will see the different channels, the different samples that loop together at the same time, and it makes quantification identification easier. Deuterium offsets this so you don't actually see the channels don't elude off the column at the exact same time. However, acquiring this data, again, 200 picograms, really low input level of Manus. On an Explorers 480, so it's now not just state-of-the-art Astral, it's a different instrument, more affordable standard instrument, or we can still achieve accurate quantitation. So this is a 6-plex for diethylation with 2 Dalton offsets, and we still maintain quantitative accuracy. As was noted previously, I guess something to acknowledge is the accuracy of this problem is highly dependent on your library. Because if you want to minimize the residuals, as we talked about, between this side of the equation and this side of the equation, you need an accurate representation of your library. And this not only includes having the correct fragment intensities, but having all the possible library entries present also. And this is something, while if you look at a label-free example, we can say, well, how similar were these both sides of the equation? In label-free, we can see they're very highly similar. So this is a measure of how well we predicted each spectrum we observed. Currently, it's slightly worse for PSM tag, but as Nikolai said in the previous questions, this is something we can address. So these label-free models have been trained on millions and millions of spectra. We are just acquiring that data. We are optimizing these libraries all the time. So the results I've shown you will inevitably get better as we get a better model of our data and therefore better library predictions. So just to conclude, Jmod enables scalable proteome depth with large plex size. So as we increase the number of samples we run parallel, we're not sacrificing the number of proteins we see. It provides accurate quantitation for single cell level inputs. So these really low level inputs, we can still get back the expected quantities we want. It affords increased throughput. So I talked today about one methodology where we use small mass offsets where we can double the throughput we can get for similar molecules. But Jason's going to follow this talk talking about another dimension we can increase throughput that is also enabled by this joint modeling approach. And so to finally just acknowledge again the people that made this happen, with the whole team at PTI who are an absolute pleasure to work with. I want to make notable note of Sarah and Maddy, who have been great in terms of helping acquire the data and giving advice in general. And of course, Jason and Nathan, who made extensive contributions to Jmod and how have been excellent to work with. And so thank you for listening. I guess to finish on, this is on GitHub. It will be publicly available in the next week or so. It's going to be at this handle. If you want, please download it, try it out, let us know what you think. You can contact it through the GitHub, or if you want to contact me, my email is there, and you can get in touch if you wish to collaborate. Thank you.
Thanks, Kevin. Let's open it up to some questions. I'll start with one. So we've seen 4 Dalton spacing, we've seen 2 Dalton spacing. What are the limitations to going smaller, like single Dalton offsets?
This is something we've explored with non-commercially available tags previously, and for the analysis we did at the time was only on bulk, and we did get accurate quantitation. So we believe it is possible. Again, I think one of the main limitations, you need accurate representations in your library once you go to that. We have a couple of improvements we have still to make, as Nikolai alluded to. This is still a work in progress. This is version 1 of Jmod and will be improved better, but theoretically there's no limitation. What you run into is if you don't have everything in your spectrum. So you have some type of peptide that is not in your library, and maybe that causes an interference in one of your channels. And now that you're at single Dalton spacing, maybe that becomes a bigger issue. But we don't see there's a huge issue with single Dalton. That's something we're going to actually explore in the next few weeks.
Question.
Kevin, great talk. So from my understanding, the quantitation is on the MS1 monoisotopic piece.
What we actually take is the start about MS2 deconvolution, but we can do the exact same principles at MS1. If I can go back. Yeah, so we can take this example. So for this is a particular MS1 spectrum. And so this joint modeling will give us a coefficient for each of these channels in this particular spectrum. And what we can do is we can do that for every single MS1 spectrum. And what you get is a series of coefficients that trace out the abundance of the peptide over time. And we just take the area underneath those coefficients as our quantity.
Right. So for the coefficients, like, have you considered adding in like external factors like the peptide length into consideration?
We take that into account in terms of so what we're actually, sorry, I should say we're fitting here is the theoretical isotopic envelope. So that will inevitably take into the peptide length because of the number of carbon 13s we have. So again, having an accurate model of that is essential for this. So that was something that's actually interesting. You bring that up. We're dealing with this is we have to take in the tags we have currently developed have their own isotopic envelope. And because they're quite large, that is significant. And so we have to actually account for that in this modeling approach because it's significant.
Got it, thank you.
Yeah, some here in the back.
Hey Kevin, thanks for the talk. So you mentioned the tags have their own envelope. Do you have a rough idea about the purity of the tags?
The purity of the tags?
Or the isotopic purity in terms of...
I believe it's pretty high. It's not a question I can answer, maybe someone else can answer, but their distribution they have a natural distribution. So I guess maybe what you're getting to is as we actually remove some of the dopable sites, the natural distribution will be actually different for the delta 16 versus the delta 0 because there are fewable natural positions that carbon 13 can hold. So in terms of purity, I think it's pretty high in terms of the actual, when we dope the sites, but then sites that are undoped still have this distribution. So we just say, okay, what is the number of sites that are undoped? What would be the natural distribution based on the carbon 13 values?
And have you found that for the Jmod workflow that the narrow window, like Astral DIA, has that been a big boost in terms of the performance that you've been seeing? Or does it, even without that fast MS2 scanning capability?
Yeah, so narrow window is an interesting example. With this Astral data, I don't have, but I think it's about 20 windows, so we're not utilizing the tiny windows that can be afforded by the Astral. But one thing to note with the Astral, say at the MS2 level, is you may not be capturing the full isotopic envelope. And this is something Nathan is working with us has discussed and we plans to implement. So if you capture only a fraction of the isotopic envelope of the precursor and then you send that for fragmentation, that will affect the fragmentation isotopic envelope. So this is something we need to model. So we actually include isotopes at the MS2 level because those are peaks we want to see. So we need to account for, okay, if we only capture part of the envelope, whether it's the start or the end, how will that impact the fragmentation isotopic envelope? So that's something we can model and predict.
Thank you.
This is going to be a basic question. In the presentation before and also in this presentation, you guys kind of talked about the difficulties with spectral libraries. Can you touch a little bit on what steps you're taking or what experiments you guys are doing to optimize those spectral libraries?
Yeah, cool. So in terms of the label-free libraries I'm using, I use ProZit, trained on hundreds of thousands, maybe millions of spectra of library-free data. There are different approaches you can train from scratch. And so we have these really large molecules, as you saw, affect chromatography. They also affect fragmentation. And so we could take a model that's already trained to predict a label-free data and fine-tune that to these to the changes we observe due to this tag. Or we could train from scratch. We currently don't have a lot of data or enough data to train from scratch, so we've been working with fine-tuning from a label-free model or from an in-track trained model. But the difficulty is, I think, that this tag, because it's so different to these others, the models struggle to actually get to that place where it's accurate. So we're currently seeing, as I showed, we can't optimize it fully, even though we have thousands of spectra, it's simply not enough. So we're currently thinking of different ways to frame the problem in terms of how do we include the tag in these prediction models. So that's one of the ways we're exploring, and how can we better fine tune these models. But yeah, it's an open question.
Maybe really quick, I know Silex sort of out of vogue with all the tagging and high multiplexing, but if you looked at the quantitative accuracy, if you just had like a 2-channel Silac, do you have a sense of how tight the distribution would be?
We did experiments, I don't have them here, no, I don't have them, where we looked at the delta 0 and delta 2 versus delta 0 and delta 4 only. So a similar example, so it's not the effect of multiplexing. And quantitative accuracy is pretty similar. So not only have you, I guess, with the 9-plex you've increased the number of peaks, well, the complexity of your samples, and so that makes fitting a bit more difficult, but if you were to just look at the two together, it's actually comparable without the effect of increased multiplex.
Any more questions from the audience?
Have you evaluated the resolution, how the resolution impact the quantitative accuracy? And for example, on the Astro, you have a very high resolution mode versus timestamp, or if the ion mobility additional dimensional separation can help you to reduce the overlapping pattern. This kind of factor how they impact the accuracy of the quantity.
Yeah, so on the basis of resolution, yeah, we do see greater quantitative accuracy on the Astro. This modeling approach is really good if you have this shared fragment. So if you've made the same ion because of the exact same partial peptide sequence, so the exact same fragment, they'll be identical in what resides. But if you have interferences now from similar peaks that are not resolvable, and you have a very high peak next to a very small, that is not something, that's just a factor that the mass spec resolution, and not something we can model correctly, because we just get centroided peaks here. That's what we model. Sorry, what was the second part of the question?
If the separation, either the gas
Oh, and
separation
sorry.
or the LC algorithm reduce the closure and help you to get better quantity.
Yeah, I don't have that data on hand. We have explored using this on timsTOF SCP. We haven't a good method of doing that. It works, but we're reliant on other software to centroid the data, which hasn't been working the best in our hands, but it's something we're actively working on. So we have this joint modeling approach working, we don't have it evaluated in this context on the ion mobility separated data. But if you can set up your problem that you're still just fitting those peaks, it's fine in that context.
Any other questions from the audience? Oh, we have one online. Okay, let me read this. Hello, sorry. I believe there's a missing word. How do these tags behave for PTM analysis, and will there be additional complexity for data analysis?
It's not something we've explored, but something we really want to look at now. As we kind of finish this 2 years, this initial phase 1, is I can't really comment on the tags in terms of this additional complexity, but this joint modeling approach, as you can see, for very similar peptides, which may be PTMs, they may, if we have wider windows, they may end up in the same spectrum. And so this joint modeling approach naturally affords us up to dealing with that kinds of data. So it's something we're excited to explore, we want to look more into and how it works. But it's not something I have data on yet, I guess, and I can't comment on how the tag will affect that.
Any other questions we have for Kevin and joint modeling? All right, well then let's give another round of applause.